Right, we've been looking at manifolds, and just a reminder, we defined our manifold as a set that is covered by a whole bunch of subsets. Each of these subsets individually have a chart or a coordinate system that maps them to Rn. Okay, we had the condition that each point in our manifold must be in at least one of these sets, and where you have a point that is in two of them, then the mapping must be consistent. In other words, if you map to this patch in Rn or Rm, and you have another chart that maps it to a different Rm, where it overlaps, and only where it overlaps, you must have this function that is one-to-one and invertible that takes this patch in Rn to that one. Okay, and that was our manifold. In other words, we were stitching together in a consistent manner the feature that you could actually map locally your manifold to Rn. And what we're going to do now is define vectors on this. Okay, so we're going to take our intuitive concept of vectors from physics, that you choose an origin and you have a way of adding and subtracting and and multiplying, and they obey vector axioms, and we're going to find a way of systematically building that up from what we already know. Now the big problem is in curved geometries all these things are lost, strictly speaking, because it makes no sense to add 2 points on a sphere and then you end up with a third point on a sphere. Okay, so we have to find a way of defining a vector, proving that it obeys the axioms of a vector space in a way that when we go back to flat space, we actually know what we mean. And so what we're going to do is we're going to recover the idea of a vector for very, very small displacements. And then we are once again going to work on finding a systematic way of stitching it together and moving vectors over the manifold. But once again here, we're going to build it up just in terms of the structure and the language we've developed so far. So what we're going to do is focus first on tangent vectors, okay? And then define tangent vectors not in terms of our external tangent plane that we had, but just in terms of the intrinsic properties of the manifold itself. Okay, and then once we've done that, we're going to have a way of doing calculus on manifolds. So once again, it's going to be abstract, but it is going to be applicable for all manifolds. So just to give you the idea of some of the notation we're going to use, suppose we have the sphere, then at each point, and initially we're going to just look at a particular point in the manifold and then define the tangent vectors at that point. That's going to be the first step, and then the next step is going to be finding a way of relating the tangent vectors at a point, say over here, to the tangent vectors at a point over there. And this just illustrates if you have a vector over here, it's very hard to actually just add it and remain on the manifold and get a vector over there. Okay, so on a two-sphere, you basically have this manifold embedded in R3, and it's got a very intuitive way of defining a vector space, sort of the idea that you have a vector on S2, okay, is simply a vector in the tangent plane to the sphere at that point, okay, and that's mathematically precise. Even that doesn't generalize easily, and we're going to find another way of actually doing this. In fact, the way we're going to find is, remember when I said, suppose you have any parameterized surface and you want to find the tangent space to it, you take the derivatives of that surface with respect to a parameter. Right, remember when we had the rule surfaces with S and U, where we had S is simply a vector that points to the points on the surface and is parameterized by S and U, then the one vector is d big S du, and the other vector is d big S ds, and those would give us vectors in the tangent space. So we're going to generalize that idea over here. So for example, if you wanted the tangent space of the sphere, what you would simply do is get that expression for your sphere and take its derivative with respect to theta, and take its derivative with respect to phi, and that would give you two vectors that are then in the tangent space. So that relationship, or that idea that your vector is associated with a derivative, is actually the thing that generalizes. Okay, so for manifolds not embedded in Rn, such as GR, we need to define a tangent vector in a way that refers only to the intrinsic structure of the manifold and not the embedding. In other words, this idea that you have your circle in 3 dimensions, just forget about the 3 dimensions. We need a way of doing it that doesn't require this picture. And the way we do it is to do exactly that identification that I did with taking the vectors as directional derivatives, and that is actually the thing that generalizes. So what we say is, in Rn, there's a one-to-one correspondence between vectors and directional derivatives. Okay. So for example, you have a vector v1 to n in Rn. Okay. That thing defines the different directional derivative operator if you dot it in with a gradient. Okay, so for every vector, you can always say, I want to have a derivative operator in a specific direction, and the vector tells you what that direction is. Okay, so that identification is the one that generalizes. Okay, and there's a one-to-one mapping. As you can see, define any vector, and you can get a directional derivative. Define any directional derivative, you'll always get the vector which tells you which components, how to combine the components of the derivative. Okay, so what we do is directional derivatives are characterized by 2 features. The one is linearity, in other words, the sum of 2 vectors gives you another vector, and the other one is Leibniz's rule. Okay, and the caveat here is this is applied if they act on functions. So intrinsically, when you have a directional derivative, you've assumed there's a function over here f that it is acting on. You don't know what the function is, but you always assume that there is a function that it acts on. Okay, so what we do to make our directional derivatives is, remember we have already this top part, we have our manifold, it has open sets, it has a chart that takes us from the manifold to Rn. Okay, and now what we want to make a directional derivative, we've got to have a function. Okay, we don't tell you what the function is, it's just the abstract idea that the function exists. In other words, and the functions are only there for the vectors to act on. Okay, so what the function we define this function f as simply a function that takes your manifold and a particular point in the manifold to something on the real line. Okay, so it's a rule of if I have a point in my manifold, okay, that I can always map to n coordinates in Rn locally, then a function takes that point and it gives me a specific value on Rn. Okay, and you can either go directly from the manifold, or you can say my chart maps this point P to a point in Rn, okay, which is the image of P, so it's phi of P. And then I have a function that actually goes from Rn to the real line that gives me the same result, but that is simply f combined with phi minus 1. Okay. So now we are in a position to actually define vectors on a manifold M in terms only of stuff we've already defined for the manifold. And the way we do it is kind of cute.
Sorry.
Yes?
I got lost.
Where did you get lost?
So we go from the point P, if we start at the point P, we apply f to go to f of P, and we apply phi to go to phi of P. So how do you combine, how do you, the composite function? I don't follow that.
Okay.
Inverse of phi.
Okay. The inverse of phi takes this image of phi back to P.
Okay, and then okay.
Okay, so you can either go, watch the arrows, you can either go from P to phi, and then you can go take the image of this thing to there, okay, or you can go minus to over there, but you've got to close the loop.
Sorry, the f function, I had the other way around.
Okay, so what this thing is over here, this is an f prime, which takes Rn to there, but it's related to the other things you've had. It's not a new entity itself. Okay. Right. So to define derivatives, all we've done is said there are a group of functions that map my manifold to Rn. Okay, that's the only thing we've added. And then what we do is we denote all possible functions, C infinity functions that map our manifold to R1, to the real line, by this collection F. Okay, so it's not a specific function, it's just all possible functions. So that's the new thing we've said exists on the manifold. It's a rule that takes the manifold to the real line. Okay, and once we've got this, we define a tangent vector V, okay, at a point P in the manifold, to be the map that takes the functions to the real line. Okay, so what you do is you say functions from M to Rn exists, and then vectors is a map that takes the functions themselves to the real line.
So it's all the f functions.
It takes all the f functions to a real line. So what this vector effectively is measuring is how these f functions change. Okay, it's basically measuring how the f functions change in the one direction and in the other direction and the next direction, and we use that feature to define what a vector is. Okay, and all of this is encompassed with our definition of what a manifold is so far. And this seems finicky, but the power of it is it generalizes and it makes it very clear to identify how vectors change and how other things change later on. Okay, so when you make proofs with this, you use only the definitions you have up until this point. It's literally building the logical structure of manifolds absolutely from a set, effectively. Okay, so this map, which we've defined to be a vector, has properties. The one, it's linear, okay, and the number two is it obeys Leibniz's rule. And those two properties are sufficient to have it reconstruct everything we know about a vector. Okay, so the fact that it's linear basically means that the vector applied to a function, a constant times one function plus another constant times the next function g, is simply equals to a constant times the vector applied to a function. And remember, this vector applied to a function basically takes the function to R plus the constant b times the vector applied to the other function g. So we're building in linearity, okay, and that's true for any function f and g, okay, and any a and b in R. So that's what the condition of linearity means. The condition of Leibniz's rule is simply what we usually know as the product rule for differentiation. Okay, so the vector applied to the product of two functions is simply the function evaluated at the point P times the vector applied to the function G plus the function of G evaluated at P plus the vector applied to the function F. Okay, so that's literally the product rule that we've seen again and again. And that, surprisingly, it's not at all obvious, but these are sufficient to define infinitesimal displacement. So there are actually very few assumptions that are going into a structure. And what's nice is it extracts the core of the structure that we're going to see later on.
Can we omit the P and just say it's the f of the v of g plus the g of the f of...
Yeah, so the P is arbitrary. Okay, it just makes it easier because you're working only at a specific point, right? We haven't yet, so that's basically what the P is telling us. It's simply if applied at P. So maybe, no, you can't omit the P, okay, because f is a function, an entity, a function. this vector applied to fg is a real number.
Okay, so if v of g is not a function of p, it's just a number.
It's a number.
Okay.
Okay, whereas, so if here on this left-hand side you need you have a number. Okay, it's v applied to this composite function. On the right-hand side you need a number. So f is a map from the manifold to the real line. So it must be applied to p. F applied to p is a number. V applied to g is another number. It's how g is effectively changing. And then g applied to p is a number because it's mapped the manifold to the real line. And v applied to f is another number. Okay, it's how f is changing in a specific direction. And yes?
Is the function f unique?
A function f is any function.
So say so we have a mapping from the manifold to Rn.
So here you have two things. You have your chart, which gives you coordinates from this thing in Rn. And then you have a function that maps from the manifold to Rn. Okay, and this is not unique. You can have several functions that map. Okay, in fact, when you define the vector, you don't use a specific function. You basically use the collection of all possible functions. Just like the derivative is acting on a function. The idea of a derivative is that it measures how a function changes. So that's what the vectors are doing. It's basically a vector is measuring how a function changes in a specific direction. And so the function actually has very little to do with it, except that if you evaluate it, you get a number. It can be any function. So let's look at an example of how to actually work with this machinery. Okay, so suppose we define a constant function, okay, h of a q to be a constant c for all q and m. Okay, so that's what we define the constant function to be as. Then what we want to say is, be careful, it's not, you can't just say the derivative of constant is 0. You've got to actually use the definitions we've been using so far. So then you can basically say 1 and 2, basically, in other words, linearity and Leibniz's rule basically implies that if h is one of these functions, one of the all possible functions, and if it is a constant function, then the vector applied to h is 0. Okay, so you can prove this. How do you prove that? Well, what you do is you use only the rules you've defined for that give you v so far. So you start with v of h times h is simply Leibniz's rule, so you write it out. So it's h evaluated at q plus v applied to h plus h evaluated at q plus v applied to h. So you get 2 of them. Okay, and you know that this thing is a number. Okay, and you know that we've defined our definition of the constant function to be equals to c. Okay, so you can immediately evaluate this side. So you have 2c times v of h. Okay, so that's the one. What the consequence of the one the one restriction on your v is. The second one has basically linearity, right? So you have v of h squared. You can say, okay, h applied to any q is equals to c. So you can replace h here, one of the h's with a c. Okay, but you cannot replace both because remember your vector is defined as mapping a function, the group of all functions to Rn. So you can only replace one. You've got to make sure your vector is always acting on a function. Okay, so here you have your vector applied to c times h, and you have linearity, so you can take the c out, so that's equals to c times v of h. And so what you now have is c times v of h is equals to 2c times v of h, which basically implies that v of h is 0. Okay, So there you have, it looks like a whole bunch of hard work, but the structure you've put in, you will see how useful it is later on when we start working with vectors. And in fact, it's so crucial to understanding what the manifolds work that you can't get rid of it. It's one of the most fundamental ideas that actually goes into structuring a manifold. Okay, so what we've done here is basically proved that if you have a constant function, a vector applied to that constant function is always 0.
Can I ask something that is a bit stupid?
No, any stupid questions allowed.
So if on the previous page where we defined the f function,
Yeah.
so those f functions that maps to real numbers, they are also not one-to-one, because we can get a constant, let's say c is 2, so then it applies to 2, but if c is to 100, it still applies the same thing. So it's not one-to-one, the different functions to each individual real number.
No, it's the functions aren't one-to-one. In other words, you can have, so what the constant function is doing is basically taking every single point on your manifold and mapping it to one number. Okay, so it's not invertible. You can't say, I have this constant function and then I'm going to go back to the point where it came from. Okay, so that's the difference between a function and a chart. Right? The function has basically taken a point on the manifold that effectively is 3 identified by n numbers, okay, which you get from the chart, and it takes that point and it collapses it into one value. Okay? And if the function is not constant, that value will change, but there is still no way of how you will be able to given the value, you're going to get back to the manifold. It's like taking, for example, the sphere, right? You can put, the sphere has 2 coordinates, theta and phi. So then you can make a function on your sphere that maps, say, cos theta plus sine phi to a specific value. But there are various causes and phi, combinations of cos and of theta and phi that will give you the same value. Okay, so generally a function from the manifold is not invertible. You can't go back. Okay, and in fact the extreme case is the constant function where you've mapped the whole manifold to a single constant. And so, yeah. Now, what we're going to do is we're going to let VP denote the collection of tangent vectors at P. So we're going to pick a specific point and we're going to look at all the possible tangent vectors we can get. We now have the properties of how to work with a tangent vector. In other words, you've always got to make sure it's got Leibniz and linearity. But now let's look at what we know about the tangent vectors. And so far, we're going to work just at a specific point. So far, we're not connecting them together. We're just working out all the properties at the specific point. And what you can show, and what we are going to show, is that VP is a vector space. Just using these definitions we've used so far, we can show that this vector applied at a point P is a vector space. In other words, it has all the properties that you have a certain number of vectors that span it. It has I'll enumerate them now. Okay, so what a vector space is basically, suppose you have 2 vectors and you apply it to a function, then it's just the vectors applied to the functions independently. Okay, so you have your addition law, and that makes sense, right? So suppose you have, if you think about V as directional derivatives, suppose you measure how V changes, F changes in the x direction. Do you want a toilet paper?
Is it a tissue?
Yeah. Suppose you can keep it close to you if you want to.
No, it's not that bad.
Okay. So suppose you have V1 is just ddx, how it changes in the x direction, and V2 is ddy, how it changes in the y direction. And you apply that to your function, then you can apply it independently to your function. Okay, so it's simply the change in the x plus the change of the y. Okay, and the second thing is you have scalar multiplication. In other words, A multiplied with V. Okay, those two together applied to F is simply the constant times V of F. Okay, and if you have that, then what you can do, and this is what we're going to prove, is that if M is an n-dimensional manifold, then, and P is an element of M, in other words, exactly the picture we've had for a specific point in M, then if VP, then we're going to let VP denote the tangent space at P. Okay, and then we're going to have that the dimensionality of VP is equals to n. We can prove this. Okay, so the vectors that we've defined as basically acting on a function from your manifold to R, okay, as a directional derivative effectively. The moment you've done that, you've basically forced vectors defined in that way to have the same dimensionality as your manifold itself. And the reason for that is basically, let's show that the dimensionality of VP is n. The way we show it is you construct a basis. Okay, so if your dimensionality of your vector space is n, then you basically have a basis of n functions that generate it. And the way we do that is we basically want to find n linearly independent vectors that span V of P. In other words, we want to find a combination of sort of the most, in some sense, independent vectors that you can make any vector in the vector space up of. Okay. And so, for example, let us begin with a chart. So if we have phi that maps our manifold to the real numbers, okay, so that's the phi we've had. So let that be a chart, and let P be a manifold in U. So P be a point in the manifold. So this is basically just writing down the picture we've always been drawing.
U is like a subset of the manifold.
Yeah, remember we defined our manifold as the set that has a whole bunch of subsets U, so that U maps to Rn. So I'm just saying, let us look at a specific U that encompasses the point P, and it has the chart phi. So it's just writing out that picture that I've been drawing. Okay, and now F is a function that goes from, is a member of all the possible functions on the manifold. And then what we're going to do is we're going to define this function that takes the image of the point P in Rn as that F circle phi minus 1. In other words, the function that goes from U. I'll draw you the picture again. The function that goes from U, the image of the big U in Rn. Okay, if we want this function, okay, then what we're going to do is for each, this is just an index that goes from 1 to n, we are going to define xu, okay, as a thing that goes from the functions to R. In other words, this is an example of a vector, remember? The vectors map from your function space to R. And we're going to define examples of that xu in the following way. We are going to define xu to be the directional derivative, right? Because of this thing that lives in Rn. Okay? So this F circle phi minus 1, evaluated at the image of your point P, how it is changing with respect to your coordinates. I'm going to say this thing will form a basis of my vector space. Okay, so what have I done? Let me finish the slide and then I'll reinterpret it according to the thing. Okay, so I have my ordinary three-dimensional manifold. I have my manifold and then I map it to Rn. Okay, so I'm mapping U to Rn. On Rn, I have a very good idea of what a directional derivative is. Like Rn is just the normal ddx in the one direction, ddy and ddz in the other direction. So what I'm doing here is I'm constructing a basis for my vector space of the manifold by using the fact that I can always get a basis in Rn just using the different directional derivatives with respect to the coordinates. Okay, so if you just think about Rn, right, I've just my Cartesian coordinates on Rn, right, there are n of them. If I want to take, I have a directional derivative in the x direction, I have a directional derivative in the y direction, directional derivative in the z direction if n is equals to 3. So what I'm doing is I'm using that fact to build up my basis in my manifold. And so these x's that I'm making up is simply using the directional derivatives that I know in Rn and applying that to the function from Rn to the real line, and I'm identifying this basis in the manifold with those directional derivatives themselves. I'll give you another picture later on. Okay, and then what I want to say is these vectors are the tangent vectors, okay, and they're linearly independent, and they're the tangent vectors of the manifold itself. So I'm literally structuring my idea of the tangent vectors in the manifold from my idea of what tangent vectors are in Rn. So let's see if I can actually get the picture. No, wait, let's go back. Sorry. Okay, so what have I done? Okay, I've defined my vector space as basically directional derivatives on this function, which I haven't given you the function. It's basically a map that maps how this function changes onto R1. Okay, and then to prove that there are n different independent ways of doing that, I said, fine, let's leave the manifold for a bit. Let's take this point P to my Rn. So I now have a function in Rn, okay, that maps Rn to the reals, and that's this composite function. Okay, so for a given P, this combined function is going to map the image of P to the real lines. Okay, so that I can call, say, a new function f prime. And that new function I can simply say, okay, because that's a function from Rn to here, I can define n different directional derivatives, namely how the function changes in the x direction, the y direction, the z direction. Okay, so that's well defined over here. And what I'm then saying is, in order to get the basis for my manifold, I'm simply going to identify the basis for my manifold with whatever function I would have gotten from the one mapping the image of the thing to Rn. Does that make sense? You're going to have to go through it carefully. But it's actually quite clever. It's literally using the idea that I have directional derivatives in Rn that I know and that are independent.
So if we say like we're going to use R3 just for
yeah.
now, and we map our basis to R1, just the real numbers.
Yeah.
It's going to be 1, 2, and 3.
Oh, no, wait. So suppose you have R3, right? Yes. So suppose you have any function, say a function of x, function of y, and function of z. Say you have a function of x, y, and z. Okay. Then what the basis for the vector space is basically the directional derivative in the x direction, the directional derivative in the y direction, and the directional derivative in the z direction. Those three, how functions in general change in the x direction, in the y direction, and the z direction, those then form the basis for your vector space in R3. And by basis, I mean any derivative in R3 can then be a constant times ddx plus a constant times ddy plus a constant times ddz. Yeah. Okay, so all the proof does, it says identify the basis of the manifold with the basis you've gotten in R3 in a one-to-one way.
Okay, so if we take the basis then of the manifold and map it to the real number line, and we take the basis that we find in Rn and map it to the real number line, they're going to...
There's a one-to-one correspondence.
So
okay.
So So the basis 1 and basis 1 on that side are both going to map to the same number.
Yes. Yeah. So, and that's literally what you've done. Okay, so here, this thing, this x of u, maps all functions on the manifold to R. And the way it maps the functions on the manifold to R is it first it looks at the point in R3, it looks, or the Rn, it looks at what point, it makes, it starts at a point phi of p, right? It maps it to Rn, and then it works out how this composite function is changing in Rn. And then it says that identification is what is actually the basis of the manifold. So this x of mu is mapping function from the manifold to R, and it is defined by using your chart to go to Rn and then mapping that to R. Okay. And you can do it in Rn because you know you have the Cartesian coordinates and you know they're independent. And so immediately, because you can construct n of these functions, you have n independent basis vectors. Okay, so then what you have is x1, xn are tangent vectors that are linearly independent because those in the Rn are linearly independent. And what we still need to basically show is that these vectors span Vp. Okay, in other words, we've shown that we can get n independent tangent vectors, so at least we have a dimensionality of n. But what we haven't showed is that any element of Vp can be expressed in terms of these vectors. Okay. You have to go. Maybe we should stop right here. Yeah, okay. It'll give you a time. Take Wald and actually read it as well. It's going to make it easier before the next lecture. So yeah, let's stop.